Welcome to the lesson 38 of industrial instrumentation. In this lesson, we will cover the control valve. In fact, this lesson 38 and 39 both will be dedicated to the control valve 1 and control valve 2. Control valve, as you know, it is a final control element in a process, and it is most important part of any industrial instrumentation. Now, so far we have studied, as you know, the many sensors which actually measure the process variable flow, temperature, pressure, viscosity, pH, or so on and so forth. Now, all this actual measurement is to basically to control some that particular process. Suppose in the case of temperatures or in the case of flow, we have to control the temperature. We have a set point. So, our goal is to to make that whatever the set points determined by or fixed by the engineers, our system should attain that particular value, right. So, some or the other we need control valve. Now, control valve is basically is a device which will resist the flow of the fluid, either liquid or gases, through a pipe, right. This is the basic purpose, and directly it is controlling the flow, indirectly it is controlling the temperatures and any other process parameters, right. Suppose I have a indirect heating of a boiler, so we are heating it by a superheated steam. In that case, by controlling the amount of steam also we can raise the temperature of the boiler. And directly in the case of flow measurement, there is no problems. We have seen that by changing the flow, that means that changing the flow through the pipe, I can control it, I can achieve some set point which is predetermined. Now, all this basically is to as you can see that this control valve is basically is a variable resistance. It will offer a variable resistance to flow. And why we are telling it control valve, because and there is a distinct difference between the valve and the control valve, because in the control valve signal will come from some controller, and it will offer some resistance, either either open the valve stem or it will down the valve stem, so that I will achieve if the desired flow is more than the what is actually existing, so that I have to open the valve. If the desired existence is less than more, then I have to close the valve. So, we can do it manually, but in the case of control valves it is done automatically, right. So, let us study this control valve in details. Lesson 38, control valve 1. The contents are introduction to the control valve, then basic control valve terminology, then we have valve sizing, because the valve sizing is also important. At the end of the lesson, the viewer will know the different components of a controller. What are the different components, what are the different terminologies you must know first, then we will go for the other details construction. What are the different flow characteristics we can achieve in a control valve? We will find there are 3 different characteristics we will achieve in the control valve. What is the valve sizing coefficient and valve discharge coefficient? These are 2 important parameters for designing a control valve. This also we will know. Basic sizing procedure for the laminar liquids and turbulent liquids, and choked flow and gases. Choked flow, you will find that most of the cases the flow is choked, so it is called choked flow, and also for the gases, because all these things we are not considering the solids here, we are at best we can consider the suspended particles in the liquid. So, this will be covered in details. Let us look at the introduction. The control valve is the most popular final control element, okay, that is the last device in a control loop, right. That means I am measuring with some sensor, okay. Suppose I have a flow meters. So, flow meters in the case of orifice meter or venturi meter or any other meters, but ultimately to control the flow in the pipe I need a valve. So, it is basically a final control element. I will measure the flow, actually existing flow. It is, if it is more than the set point, okay. So, I will close the I will reduce the flow through the pipe by the control valve. If it is less than the desired value, so I will open it so that the more flow can go. So, ultimately, so that is the reason we are calling it a final control element in any process. The control valve manipulates a flowing fluid such as gas, water, steam or chemical compounds to compensate for the load disturbance and keep the regulated process variables as close as possible to the desired set point. Now this question may come, that several times I am saying that if it is more, if it is less, why it will be like this one? Because I have a set point, okay, is not it? So I know that the flow should be suppose 10 to the power 3 liter per hour. So why should it change? Because I have already set points, I have some pump which is flowing to the, which is pumping the liquid to the pipe. So why should it change? It will change due to the load disturbances. So due to the load disturbances, if it changes, so I have to open the control valve, I have to close the control valve, so that the whatever the desired flow of liquid, what are the set points already there, so liquid should flow accordingly through the pipe, right. A control valve is selected on the basis of the process control system requirements and the characteristics of the process fluid, right. There are different types of control system requirements. First of all, you have to look at, and you have to look at the process fluid, what type of fluid it is, whether it is a clean fluid, whether it is a dirty fluid, whether it is a very highly viscous fluid. So all this depends, considerations you have to keep in mind to choose a control valve, okay, or control valve characteristics I should say. Now you see, this is a basic control valve, you can see here, you see this is a control valve. Now you see here that we have a pneumatic control valve, we have a bonnet here, okay, you see here there is a diaphragm, okay, and let me take a different color. I have a diaphragm here, and this is called, you see, this is called the plug of the control valve. The liquid fluid is coming, either gas, or anything is coming through this, and it is going out through this one, right. And you see there here that there is a plug, and this is called the seat of the control valve. This is called the seat, this is plug, and this vertical this is called the stem of the control valve. You see this portions I am talking about, this is this portion, this is called the stem of the control valve. You can see here, this is called the stem of the control valve. Here you see there is a packing. This packing is necessary so that the valve, this stem can move only in the vertical directions, as well as it will resist the flow of the fluid through this portion. Liquid will flow, come this one, according to the openings it will come to this one and it will fluid out, it will go out like this one, clear. And we have a bonnet here. A spring is necessary, because when you when it is removed, when the pressure is removed, that means when if the pressure from this pneumatic signal is removed, so valve should, this stem should go to its previous position. This type of valve you can see, it is called air to close, because the air is to be come through, pneumatic signal will come through this one and it will close it. So this is called air to close valve, right. And this is the cage, and this is the packing, as I told you. This is a spring which is needed to move the stem of the control valve to the position when it was normally, when there is no pneumatic signal there. So this type of control valve, when there is no pneumatic signal, so the valve will be fully open. Okay, so to give the full pressure, so once you give the full pressures here and through the pneumatic signal, because this is totally sealed, this is circular in shape, so the seat will be, and the valve stem will sit on will come on the seat of the control valve, right. And this is the fluid, and liquid is flowing through this one and is coming out this one. This is the total details of a typical control valve. Now there is different shape of this plug. You will find that if you choose a different shape of the plug, I can get a different types of characteristics, that means linear characteristics, equal percentage characteristics, quick opening characteristics, depends on the plug, what is the shape of the plug. We will go through details of that one. This is the control valve. Previously what I have discussed, it is called a single seat valve, but here we have a double seat valve. The double seat valve has I have not drawn the full, I have drawn only the stem and all these things. Double seated valve also necessary for many applications. Fine. Bonnet, it is a portion of the valve that contains the packing box and the stem seal and can guide the stem, right. As I told you, if I look at, okay, bonnet, this is called the bonnet, right. It provides the principal opening to the body cavity for assembly of the internal parts, or it can be an integral part of the valve body. Okay, it can be of the integral part of the valve body. It can also provide for the attachment of the actuator to the valve body. Clear? Typical bonnets are bolted, threaded and welded pressure seals, because these are to be totally sealed, otherwise there will be a problem. Cage is another part of the control valve. What is cage? A part of a valve that surrounds the plug seat, and it can provide the flow characterization, right. So, the plug and the seat, which I have shown several times, so that is actually contains that is make the cage of the control, through which the liquid is flowing. It is coming to the in path, fluid in path, and it is going out of the fluid out path, right. So, it can provide the flow characterizations. What type of characterizations you want, that can be determined by this one. It also provides stability, guiding, balance and alignment, and facilitates assembly of the other parts of the valve, right. The walls of the cage contain openings for inlet and outlet of the valve flow. We have shown this one. So, through one it is the inlet, the valve is coming, and through which the valve is going out. Diaphragm. It is a flexible pressure responsive element that transmits force to the stem, right. It is a flexible pressure responsive element that transmits force to the stem. It is at the top of the control valve. It is a steel diaphragm. We have already studied diaphragm, gauges, all these things. This is basically giving the force to the against the spring, which is already in existence, to the stem, so that the stem will move down as well as plug will move down. It will go on and put on the cover the seat of the control valve. Plug. It controls the volumetric or mass flow of the fluid through the cage. It controls the volumetric or mass flow of the fluid through the cage. Port. These are the openings through which the fluid will flow in and flow out of the valve. Okay. Seat. It is the area of the contact between the closed member of the cage and its mating surface. Already we have shown this seat. Actually, there is a contact between, there is always when the valve, when the plug totally rests on the seat, that is, it is totally closed. When it is fully open, so that totally liquid through the, so the through the seat actually always the liquid is flowing. In between the space, in between the space in between the seat and the plug, the liquid is flowing through the valve. Trim. The internal components like plug, seat and stem that modulate the flow of the control fluids are collectively called as a stem. So, the plug, seat and the stem of the control valve, that are collectively called as a stem. The part that connects the diaphragm to the final control element. Final control element here in this case of the control valve is the plug. So, when the plug is connected to the diaphragm through the stem, okay, and the stem is surrounded by a spring. Now, basic control valve terminologies. Control valve assembly, it includes all the components normally mounted on the control valve, like the valve body, assembly, actuator, positioner, transducer, limit switches, etc. Flow characteristics. The flow characteristics of a control valve is the relationship between the flow rate through the valve as the stem travels from 0 to 100%. This traveling of the stem is called, in the process control industry, we call it the lift of the valve, okay, percentage lift of the valve. Okay. If the valve is fully open, that means it is 100% traveled, okay, like this one. That there are two types of flow characteristics. One is the inherent flow characteristics, and that is the installed flow characteristics. We will study this in details. Inherent flow characteristics we will study in more details, you will find. Inherent flow characteristics, it is the relationship between the valve flow capacity and the stem travel. When the stem travel is, as I told you repeatedly, it is basically the percentage lift of the stem, right, that is called the stem travel. Stem travel when the differential pressure drop across the valve is held constant, right. I will repeat, it is the relationship between the valve flow capacity and the stem travel when the differential pressure drop across the valve is held constant. These characteristics are plotted on a curve where the horizontal axis is labeled in percentage movement of the stem, okay, percentage horizontal axis stem, and the valve axis and the vertical axis is labeled as the percentage flow as shown in figure 3. Okay. Percentage level or lift, as I told you, as shown in figure 3. There are basically three types of inherent flow characteristics. You will find there are three types of basic inherent flow characteristics. These are equal percentage, linear, and the quick opening. We will see this in details. Linear flow characteristics. Here the flow rate is directly proportional to the amount of valve stem plug movement. Okay, there is a direct relationship. It's a linear. In other words, change of flow rate is constant with respect to the valve plug movement. Okay, it is a linear curve. There is nothing too much to say. Valve with linear characteristics are often specified for liquid level and for flow control application requiring constant gain. If you need it constant gain, that type of things, in that type of situations, I need this type of linear characteristics. We see here that you see that this is equal percentage valve, equal percentage characteristics. This is a linear characteristics. Gain is same in all places, and whereas this is a quick opening characteristics. Here this is a percent of movement lift of the plug, and this is a percent of maximum flow. This is 100% flow, this is 100% lift, 100% movement of the plug. Okay. So obviously when the valve will be fully open, okay, the stem is fully open, so there should be 100% flow of the fluid through the valve. So this is the inherent flow characteristic, valve characteristics of the control valve. Equal percentage flow characteristics. We already discussed the linear characteristics. Let us look at the equal percentage characteristics. For equal increment of the valve plug travel, for the change in flow rate may be expressed as a constant percentage of the flow rate at the time of change. Okay. Gain is not same, but it is equal increment valve plug of a valve plug travel. The change in the flow rate may be expressed as a constant percent of the flow rate at the time of change. The change in flow rate observed regarding the travel will be relatively small when the valve plug is near its seat, and relatively high when the valve plug is wide open. Okay. So near the seat it is low, and when it is valve plug relatively high when the valve plug is wide open. Therefore, a valve with an inherent equal percentage flow characteristic provides precise throttling control through the lower portion of the travel range and rapidly increasing capacity as the valve plug nears the wide open position. Clear? These valves are used in pressure control applications, since a large amount of the pressure drop is normally absorbed by the system itself, with only a relatively small amount is available at the control valve. Okay, this is applications because there is various kinds of applications. As I told you, for the pressure control, so this type of equal percentage valve will be more acceptable. You can see the characteristics, how the characteristics looks like. As I told you, if I take a blank page, it will look like this is our stem movement or stem lift. Okay, this is our flow, percentage flow, percentage lift. So characteristics will be like this one, 100%. This is 100% of the lift. 100% say characteristics of the lift, this one. Okay. So that is the reason we are call it equal percentage. Percentage will be equal at that point of the stem lift. Clear? These valves are used in pressure control applications, since a large amount of pressure drop is normally absorbed by the system itself, with only a relatively small amount is available at the control valve. These valves are also used in application where highly varying pressure drop condition can be expected. Okay. So different applications are there where we are using this type of different types of control valve. Equal percentage is the most common valve characteristic, since in most physical system the inlet pressure decreases as the rate of flow increases. As the rate of flow increases, the inlet pressure decreases. So it will be suitable for that type of applications. Now third one is a quick, third one of the inherent valve characteristics is the quick opening flow characteristics. Okay. What is this? Let us look at. Here there is a maximum change in flow rate when the plug is near the seat. Okay. And slowly it will get saturated. Clear? However, it is very simple, you see here. In the case of quick opening, again percentage lift of the stem, and this is a percentage flow, this is 100%, this is 100%, right. So, it at the initially there is a large change, slowly it will saturate like this one. For a small change here, if small change of the leaf, there is a large change of flow, slowly it will saturate. In many applications we need this type of valve characteristics. Okay. So, please note that we have three types of inherent valve characteristics. One is the linear characteristics. In some applications we need it where the gain is equal, whereas equal percentage at particular point of lift, the percentage of the valve opening will be, percentage of the flow will be equal. And in the case of quick opening, okay, that the initially it is when the valve is when the seat is very near to the plug is very near to the seat, you will find there is a large flow, and whenever the plug is coming out going far from the seat, as we move the stem upward, so there will be a little change of the flow even though there is a change in the stem position. Okay, that is basically quick opening characteristics. Here there is a maximum change in flow rate when the plug is near the seat. The curve is basically linear through the first 45% of the valve plug travel, then it almost saturates to indicate that the little increase of flow rate occurs as the travel approaches the wide open position. All is very nicely drawn in figure 3, you can look at. Control valves with quick opening flow characteristics are mostly used for on-off applications where significant flow rate has to be established quickly as the valve begins to flow, right. In the on-off characteristics we need this type of thing. The linearity which is observed in the early part of the curve decreases sharply after the flow area generated by the valve plug travels equals to the flow area of the port, right. This is actually as I told you earlier that this is the actual shape of the plug, seat will remain same, the shape of the plug will give us these different flow characteristics, right, flow characteristics through the versus the lift of the stem, okay. All these flow characteristics are in corresponding to the lift of the stem actually. On the x-axis we have drawn the lift of the stem is basically the movement of the plug, is not it. So, the movement of the plug we are plotting in the x-axis, percentage movement of the plug we are plotting in the x-axis, and percentage of the flow we are plotting in the y-axis. Now, you see all this actually basically all this linear equal percentage and as the quick opening depends on the type of plug, how you shape the plug, okay, though seat will remain same. This is a linear, you see this is a linear characteristics, this is equal percentage and this is a quick opening, right. So, this the actual characteristic, this is different shape of the plug will give us a different flow characteristics in inherent valve characteristics, clear. Mathematical derivation, let us look at the mathematical derivations. In general, the flow through a control valve for a particular fluid at a given temperature is a function of S, P1 and P2. Okay. Let us look at the legend. Q, which I am saying that the flow at any particular flow rate or volumetric flow is a function of S, P1, P2. What is S? Let us look at where Q is a volumetric flow rate, S is a valve stem position or lift, okay. Stem position, stem movement, lift, these are all basically same. In many process book you will find we have expressed as a percentage lift, or basically here for ease of understanding I am writing as a stem movement, clear. So, stem movement and lift, please note these are the two same thing. Then P1 is a upstream pressure, okay, of the valve, okay, because liquid is flowing through the restriction there will be a pressure drop across the valve. Please note there is a sufficient pressure drop across the valve. So, in the P1 and P2, P1 is the upstream pressure and P2 is the downstream pressure. That means that in pressure, static pressure of the liquid and in the upstream at the inlet and is at the static pressure of the liquid or fluid at the outlet of the control valve, right. These are we are designating at P1 and P2 respectively. For inherent flow characteristics, P1 and P2 are constant, okay. Hence, Q is a function of S only. If the pressure drop is constant, then I can say if this is constant, so Q, the volumetric flow rate will depend on S. That means Q is a function of S. What is S? S is the valve stem movement or movement of the plug, clear. Now, I suppose that if I introduce a factor capital F equal to Q upon Q max, okay, Q max and X equal to S by S max, okay. What is this? Where Q max is the maximum flow and q is the flow at any instant of time. So, this m is variable, f is variable depending on the position of the stem or particular liquid amount of liquid is flowing through the. S max is the maximum lift of the valve stem and S is a fraction of that. So, if you take the ratio, so it will give you the percentage of the flow, right, percentage of lift. X is the percentage of lift and F is actually the percentage of flow, right. When Q equal to Q max, F will be 100% and X, when S equal to S max, X will be 100%. That means valve has totally open, valve is totally open. X is a fraction of the maximum lift and F is a fraction of the maximum flow. Clear? Now, sensitivity we defined as a fractional change in flow upon fractional change in stem position. Fractional change in flow upon the fractional change in stem position will give you the df by dx, derivative of f with respect to x. For linear valve, df by dx equal to alpha. df by dx equal to alpha for linear valve, equation number 3. Integrating equation 3 within the limits f equal to 0 at x equal to 0, we are assuming that at 0, that means when the valve is totally shut off, there is no flow, and f equal to 1 at x equal to, f will be maximum flow when maximum value of x can be only the 1, is not it, because when the totally valve is moved up, the stem is moved up, so that is 1, fully open, 100% open. And at that time the flow is 100%, so of f is obviously 1, right. With this limit I can write integral df, 1 integrations of df, derivative of f, integration from 1 to 0, because f can vary, df can vary only from 1 to 0, into alpha into dx, where the limit is 1 to 0 again. Integrating these equations and putting the limits and knowing that x equal to 1, excuse me, in f equal to 1, we get alpha equal to 1, right. Putting alpha 1 in equation 3, we get f equal to x. So, this is the linear valve, right. So, this is the relations when the valve will make like this one. So, the f equal to x, that means for any position, whenever I am getting some position, so f by x is always a constant. Please note, for any position the amount of flow, if you divide it, so the gain will be constant. So, it is the linear valve. Now, for the equal percentage valve, it is slightly different. We are defining as derivative of f with respect to x, that means derivative of flow with respect to fraction of the flow with respect to fraction of the stem position will be mu into t, where mu is a constant. Integrating equation 4, we get df by f, where varies from f to f naught, and mu into dx when x to 0, right. For natural log, if I integrate, it will be f by f naught equal to mu into x, right, where f naught is the flow at x equal to 0. This is very interesting. You see, the actually the initially the linear valve, what we have assumed, that is not exactly true. A control valve will never used for totally shut off the liquid flow. There will be always some liquid flow through the control valve, right. So, we are assuming that especially in the single seated valve, this always will be true, or double seated valve rather I should say, this is always true. That means x equal to 0, f naught, we have to assume, otherwise we cannot solve the equation, right. That means at x equal to 0, that means when the valve is at the minimum position, there is this is not a totally shut off, there is a non-zero value of f, which is f naught. It is true for most of the practically in all the cases of the valve, especially the double seated valve, otherwise you cannot calculate. Equation 5 is the reason why equal percentage valve is also called the logarithmic valve. The basis for calling the above type of valve equal percentage is explained below. Rearranging equation 4 in the form, you see d by df by f equal to mu into dx, or delta f by f equal to mu into delta x, equation number 6. From equation 6, it can be seen that an equal percentage change in flow delta f by f occurs for a specified increment of change in stem position delta x, regardless of where the change in stem position occurs along the characteristics curve. Okay. It does not matter. So, if I plot it in the semi-log graph paper, what will happen? You will find it is a linear characteristics, right. I have drawn in the linear graph. If I draw in a semi-log graph paper, it will be linear characteristic. That is the reason it is telling that it can be seen that the equal percentage change in flow delta f by f occurs for a specified increment of change in stem position delta x, regardless of where the change in the stem position. Okay, let us go back and see. You see here 6. For certain change in the stem position, okay, percentage change of the flow will be constant mu, because delta F by delta x will be equal to mu, which is a constant. Clear? That is the reason we are calling it equal percentage valve. Clear? Now we are talked about inherent valve characteristics. Let us come to the installed valve characteristics or installed characteristics. The relationship between the flow rate and the travel of the plug as it is moved from the closed position to fully open position is influenced by the varying process conditions. Okay, this again the process, because so far we have not considered the process condition, but this will also depend on the process conditions, right. Inherent valve gain, it is the magnitude ratio of the change in the flow through the valve to the change in the stem position under condition of the constant pressure. It is equal to the slope of the inherent characteristics curve at any travel point, right. Mathematically, inherent valve gain can be written as change in flow upon change in stem positions or change in lift. It is the slope of the inherent characteristics curve, right. Installed valve gain, it is the magnitude ratio of the change in the flow through the valve to the change in the valve gain relationship that occurs when the valve is installed in a specific system and the pressure drop is allowed to change naturally according to the dictates of the system. Initially we have assumed the pressure drop will remain constant. It is a function of the valve gain and is equal to the slope of the installed characteristics curve. Now failed close, so far we have considered, we have seen that the failed open valve, right. So it is a failed closed. A valve condition in which the valve closure member moves to a closed position when the actuating energy source fails. Okay. In case of pneumatic valve where the actuating signal is air, such condition is air to open, right. It is called air to open, right. If the air supply below the diaphragm is lost, then the valve will be fully closed, fail closed, since the spring would push the stem in the valve down. You see here is a spring, so that what will happen, you see, if I move the, otherwise what will happen, you see that valve will be always fully open. Sorry, if I give a air here, then what will happen, because there is a spring, it will try to open, right. So it is a fail close or air to open. So I have to, spring will be always closed like this one. Okay. Now what I have to do, I have to give a pressure so that it will move up. Clear. So this is a air to close, because due to spring actions valve will be always closed like this one, because spring will be always like this one. Now if I put the pressure, what will happen, because the spring will never be in this position, it will be always in a squeezed position, right. Got it, like this one, spring will be like this one. So if I give the air, spring will be like this one. So what will happen if this is the position, let us go back, let us see. If it is that position, what will happen, you see, valve will be fully closed. Now if I put the air, so valve will be fully open. Now fail open, a condition in which the valve closure member moves to an open position when the actuating energy source fails. When the actuating energy source fails, a condition in which the valve closed member moves to an open position when the actuating energy source fails. So it is actually air to close. This is a normal valve which we have shown, and if the air supply above the diaphragm is lost, then the valve will be fail open, since the spring would push the stem and plug upwards. How does it look? You see here, what will happen, that if the valve, if the air supply fails, if the air supply fails, the spring will move the valve in the upward position, right. So it will move in these downward conditions. Rangeability. Rangeability is the ratio of the maximum to minimum controllable flow. Valve coefficient Cb, it is the number of gallons per minute of 60 degree Fahrenheit water that will pass through the valve opening with a pressure drop of 1 psi, and it is the measure of capacity of the valve, and hence is also called the capacity factor of the valve, right. CV is equal to Q upon square root of delta P, where Q equal to the flow rate in gallon per minute and delta P is the pressure drop in PSI. Now, the valve discharge coefficient, it indicates the relative capacity between the different valves and is defined in terms of CB of the valve and then its diameter D as CD CB by D square. Let us go back. I think if you have any confusions. Here what will happen, you see the valve will be always closed like this one, because I am sorry, because this spring will always try to open. If it is open, then what will happen? Okay, it will, the movement, the stem will, this seat will, this valve plug will always sit on the seat. There is a seat, so valve will always close the flow, right. Normally if there is no air pressure, spring will try to open, clear. This spring will try to open, right. If there is, and let me take this one, so spring will try to open like this one, I am saying like this, okay. Normally if there is no air pressure, suppose there is no air, then what will happen, spring will try to open. So what will it will push the stem downwards, so that if the stem, so this plug will totally sit totally on the seat, so there is no flow of fluid, air or liquid through the this region. Now if I put the air, then what will happen, okay. So the stem will move up, if the stem, this stem will move up, because diaphragm that time will be go up, so the stem will move up, so the liquid will start to flow through this one. So this type of thing is called the air to open, okay. And next whatever I have shown is called air to close, that we have seen. That's if normally it is spring will always try to move, is expand, it is like this one, spring will always try to move in this direction, okay, normally when there is no air, okay. So it will open it, because if there is fixed here, if it is, we have a plug here, okay, so it will move upwards, right. If the plug, it cannot move this direction, there is a diaphragm here, okay, so it will move upwards. Now if I want to, so the valve is fully open. Now once we give the pneumatic pressure, what will happen, this spring will now start to squeeze, okay, the diaphragm is there, spring will start to squeeze and it will totally choke the flow, right. So this type is called air to close, clear. Let us go back again. Valve discharge coefficient, it indicates that the relative capacity between the different valves and is defined in terms of CV of the valve and its diameter D as CD equal to CV upon D square. Valve sizing, Instrumentation Society of America ISA put forward a standardized guidelines for control valve sizing. The basic equation used for control valve sizing is Q equal to CV root over P1 under the square P1 minus P2 upon G under the square root, which is equation number 7, where Q is the volumetric flow rate, CV is the valve sizing coefficient determined by testing, P1 is the upstream pressure, P2 is the downstream pressure, and G is the liquid specific gravity, clear. Valve sizing procedure for normal liquid flow, we can take the simplest case of liquid flow involves the basic equation. Rearranging equation 7, we can get CV equal to Q upon under the square P1 minus P2 by G under the square root, right. Based on a given flow rate and the pressure drop, a required CV value has been calculated. This is very important, this is called characteristics of the valve, right. The CV is then compared to the CV values for a particular valve size and valve design, and a particular valve is selected, okay. So that from the series of we have a valve, so that we have to select a particular valve from that, right. First we will calculate CV and compare it with the standard CV of the valves, available valves in the process. So we will choose a particular valve whose CV will match with the CV which you have calculated. The required CV should fall in the range between 70 to 90% of the selected valve CV capability, okay. Not exactly same, it is within that range, because ultimately we will find this CV again, right. For selecting the valve along with the CV, minimum and maximum flow pressure condition should be considered, okay. That is also should be considered, static pressures. The above equation covers the condition governed by the test assumptions. Unfortunately, many applications fall outside these bounds and hence certain correction factors have to be incorporated. So, okay. If I include that these factors when incorporated, change the form of the equations as follows. Q CV valve discharge coefficient is equal to Q upon N FP FR under the square root P1 minus P2 by G, okay. What is that? where n is the numerical coefficient for unit conversion, Fp is the correction factor, Fr is the function of Renault number and describes the degree of turbulent flow. For laminar flow, Fr equal to 1, and finding n can be selected based on the following table. So, you have to, there is a table, from it you can find the value of n. This is the table you can see for volumetric flow, what is the value of n we have seen, different values of n's are there. Okay, as you say, it is a correction factor. So, if it is in kilopascal, Q is in meter cube per hour, pressure is kilopascal, so n will be 0.865. Okay, and if it is meter cube per hour and pressure is in bar, so it is 0.86. That is unit conversion, nothing else. Please note, it is just unit conversion, and it is 1 if it is Q is volumetric flow is gallon per minute and PSI absolute, right, pounds per square inch. Now, this is for the volumetric flow rate, okay, and for the mass flow rate we will choose if it is P is in kilopascal, gamma which is the density is kg per meter cube, then the weight is kg because it is the mass flow rate, so it is a kg per hour. Okay, if the pressure is in bar and is kg per meter cube, then the mass flow rate is kg per hour, that time is 27.3 we will choose. And if it is in FPS unit, that means if it is in PSI, pressure is PSI, pressure drop is PSI absolute, and gamma is pound for feet cube, that time the volumetric flow mass flow rate is pound per hour. So, we are taking 63.3. N3 value is a small d and capital D, this might be either in millimeter or in inch. So, in that case if it is in inch, a millimeter it is 0.0021, and it is inch 0.890, right. So, this will give you the conversion factors, okay, so which we will use for this value of n. This will simplify our problem solving because some countries using some, if you import some valve from US, they have some APS units, and if you from Europe we are using SI units. So, this chart will help you to find the value of n, which particular value of n will you use, okay, which particular units of Q and P you will use. For volumetric flow rate, I can write CV Q upon N1 Fp Q upon N1 Fp under the square root P1 minus P2 by G. G is a specific gravity as I told you. And for mass flow rate, so we are writing Q N2 Fp under the square root P1 minus P2 into gamma. Gamma in that case will be density. Calculating Fp. Fp is the correction factor that accounts for the pressure losses due to the pipe fittings such as reducers, elbows, because all the valves it must be preceded by some elbows, some reducers. Suppose the valve sizing is not matching with the pipe diameter, so you have to use a reducers, okay, which are attached directly to the control valve. Okay, these are all will be attached to the control valve because not necessarily you will get exactly the pipe diameter and the inlet diameter of the valve same. So, I have to use some reducers. If no such connections are made, then Fp equal to 1. Okay, if there is no connections are made, if there is no such reducers, elbows, but obviously Fp will never be 1. We will always some reducers, some elbows, something like that. Fp can be determined experimentally by using the specified valve in actual test. So, the line test or the lane calibrations we have to do. Alternatively, Fp can be determined mathematically using the following equations. What is this equations? Fp equal to 1 plus summation small k n3 into Cv by d square whole square, okay, under the square root to the power minus half, right. So, it is 1 by square root of this one, right. N3 is a numerical constant found in equation constant table. We have already seen that in what is N3, either in millimeter, it depends on the what type d and small d and d you are using, either in millimeter or inch. Accordingly, you will choose the value of N3. D is the assumed nominal valve size, which is always less than capital D, which is the Cv is the valve sizing coefficient at 100% trouble for the assumed valve size, right. That means valve is fully open. Cv when we are talking about, please note it is the valve is fully open, that is steam is totally moved, there is a full flow of liquid through the valve. Summation k is the algebraic sum of the velocity head loss coefficients of all the fittings that are attached to the control valve. Small k equal to k1 plus k2 plus Kb1 minus Kb2, this is equation number 13. What is that? Where K1 is the resistance coefficient of upstream fittings, K2 is the resistance coefficient of downstream fittings, okay. Kb1 is the inlet Bernoulli's coefficient and Kb2 is the outlet Bernoulli's coefficient. So, this will make you summation K, right. Now, the Bernoulli's coefficient Kb1 and Kb2 are used only when the diameter of the pipe approaching the valve is different from the diameter of the pipe leaving the valve, okay. If the two valve diameter is same, or pipe diameter of the pipe same, at the inlet and the outlet of the valve is same, I do not have to use, then Kb1 will be equal to Kb2, otherwise it will be different. But most of the process cases we will find this will be 0, because Kb1 minus will be equal to Kb2. So, Kb1 and minus Kb2 will be 0. So, these two terms and the last two terms can be cancelled, whereby Kb1 or Kb2 equal to 1 minus small d by d to the power 4, right, where d is the nominal valve sizing and d is the internal diameters of the piping, right. Diameter of the piping, obviously d is always greater than that small d. If inlet and outlet pipings are of equal size, then we can say inlet and outlet piping to the valve or to and from the valve will be, then Kb1 will be Kb2, hence they are dropped in such a situation. So, for inlet reducers I can write K1 equal to 0.51 minus d square upon capital D square to the power whole square, and for outlet reducers I can write K2 equal to 1 minus small d square by capital D square to the power whole square, which is 15.b equations. For a valve installed between identical reducers, I can write K1 plus K2 equal to 1.5 multiplied by 1 minus d square upon small d square by capital D square to the power whole square. This is equation number 16. For choke flow, you see that actually in the process we will find there is a choke flow. That means even though I am expecting that the flow will be always, if I use a delta P, okay, if increase the delta P, okay, the flow through the fluid in gallon per minute or whatever it may be, when the liter per hour or whatever it will increase, it will not increase, okay. So, it will saturate, so that even though increasing the delta P differential pressure, okay, will not increase the flow through the pipe. So, this regions we are calling it choked flow, right. Is delta P allowable and actual delta P is C. So, the predicted using the actual delta P, this is a choke flow we are talking about. A plot of basic equations of figure 7 gives that the relationship hold, what is figure 7? Okay. A plot of basic equations of figure 7 gives that the relationship hold only for a limited range, okay. For the limited range this will have in, otherwise it will not. At the pressure differential, as the pressure differential is increased, a point is reached where the realized flow increase is less than the expected, okay. That means there is saturation or there is a valid sort of characteristics, and finally it saturates to a particular value, right. So, as we increase, unlike the stem movement, when if you make stem movement, if you make the change of stem, do not confuse with the stem movement, okay. X axis now we are plotting, please go back, x axis we are plotting delta P differential pressure, we are increasing differential pressure in this direction, okay. We are increasing the differential pressure, increasing the differential pressure in these directions, okay. We are now in the case of the valve characteristics we have seen that the valve this seat your plug characteristics we have seen, as you increase the stem movement, as you increase the lift of the valve, obviously the flow is increased, okay. It saturates little bits in the case of quick opening, but in the other case linear and another equal percent is always increasing, right. But that is not the situations here when you are having a choke flow. That means if you increase delta P, not necessarily it will predict it, it will saturate after some time. As the pressure differential is increased, a point is reached when the where the realized flow increase less than the expected, and finally it saturates to a particular value. Any increase in delta P after that has no effect on the volumetric flow rate. Even if you increase it, that will not affect the flow rate of the valve, unlike, as I told you several times, that unlike the stem movement, whenever you have a stem movement there is always a change of flow, right. This is necessary also. This phenomena is known as the choke flow, okay. This is called the choke flow of the pipe. That means if I go where whichever one is the choke flow, this portion is called, we are calling it choke flow. You see, this is the choke flow region, right. Even though I am increasing, it is flow is not increasing, it is getting saturated. Clear? So, this phenomena is known as the choke flow of the fluid in a control valve. Clear? In such cases, maximum flow rate and the pressure drop conditions are very important. Okay? What is the pressure drop conditions and the maximum flow? These two you have to think of. These are very important in this particular cases. Clear? You have to think of this thing. Do not confuse the two. I mean, it is the leaf turn. So, maximum flow rate Q max equal to N1 FL CV and under the square root P1 minus delta F FF PV upon G is equation number 17, where FL is the rated liquid pressure recovery factor, which is actually because you know the liquid will always the pressure will be recovered, recovery factor. FF is the liquid critical pressure ratio factor, and P1 is the upstream absolute static pressure. This is very important, upstream pressures, absolute static pressures. Okay. I mean, it's here you see that we are not considering the differential pressure. PV is the absolute vapor pressure of the liquid at the inlet temperatures. Okay, this will make the maximum flow rate Q max. So, maximum allowable pressure drop, which is to be calculated, delta P max equal to FL square, which is P1 minus FF into PV. It is equation number 18. Gas and steam sizing. The procedures for sizing when the process fluid is liquid, air, gas are closely parallel. These are almost same, and is not much of difference. The only additional steps involve the correction of the physical properties of the particular gas and pressure ratio factors, which determine the degree of the compressions and predicted choke flow. Okay, that's I mean these are the only factors which is to be included, which you have to think of, otherwise not. The general form of the sizing equations for the compressible fluid is, you see CV equal to Q upon N FP P1 Y root over X upon G T1 into Z, equation number 19, where the legends are X is the ratio of the pressure drop to upstream absolute static pressure, okay, ratio of the pressure drop to upstream absolute static pressure. That is the reason we are interested in P1. The previous equation number 18 also we have seen that there is a P1 is important, not the P2. Y is the expansion factor ratio of the flow coefficient for a gas to that for a liquid at the same Reynolds number. Z is the compressibility factor, and T1 is the upstream fluid temperature in Kelvin. Okay. So, all these things, all the legends are defined. Now, every time you see that a CV is the most important thing in the valve parameters, there is no other, because if you define CV or if you find CV, all other parameters will be automatically fixed. There are some parameters like small d, capital D. So, first in the while you are choosing the valve, first I have to calculate the what are the desired CV you want for a particular applications. Once you find a CV, so from the selected list of the valve, so you try to choose CV which will match very close. You may not get the exact match, you repeat 70 to 90% of the value of the CV which you have seen, that will be the desired range of the control valve. Okay. So, that particular control valve is to be chosen and is to be installed in the process. Now, with this we will cover this in industry, I mean this control valve, we will continue this control valve in the lesson number 39 also. We will go further details and we will solve some problems in the lesson 39. So, at this with this I come to the end of the lesson 38 of industrial instrumentation. Welcome to the lesson 39 of industrial instrumentation. In this lesson, we will continue with the control valve. So, control valve we had started in lesson number 38. So, in the lesson 39 also we will continue. We will go in the deep details of control valves, because as I told you earlier that the control valves actually means the final control element in any industrial process. There actually the whatever the measurements techniques we have seen or we have studied so far, like temperature, pressure, flow, pH, humidity, so on and so forth. You will see that ultimately is to all these things are basically these measurements are necessary to control the temperature, control the flow, control the process parameters. So, basically I mean either you can make the heater power control, but most of the cases we will find that we have to control the flow, whether it is gas, fluid, it does not matter. So, we will control the flow. So, by controlling the flow I can control the temperature, by controlling the flow I can control the level and so on. So, we will continue with the control valves. So, this is the control valve 2 of lesson 39. Let us look at the contents. Control valve 2 contents are types of control valves. Okay. We have seen that we have last time in 38 we have seen that we have considered they are the equal percentage valve, then quick opening, linear, but those are not the types of control valve. Those are basically the characteristics of the control valve. I mean flow characteristics by the versus the stem movement. I mean if you vary the stem movement, how your flow characteristics varies, accordingly you can lay equal percentage linear or quick opening. But the overall the different types of control valves are available in industry. So, we will study those in details in this particular lesson. Types of control valve. So, this is all about I am talk about this I mean valve positions and all these things. You see here these arms attached to the stem to sense the valve position, and this is arms which is sense the stem of the valve position, because this will go to parallel, and this is the valve position, a signal from the PC will come, right. And as shown in figure 11, a typical valve positioners has the following features. What are the features of the valve positioners? Let us look at a set point that calls for a desired stem position from the primary controller PC. Okay, it is coming from the primary controller. A measurement in the form of stem position x. Okay. So, these two will be these two will be compared. This PC will be compared with S, obviously PC will be compared with x in a valve position. Accordingly, it will generate a control signal PV, which will go to the diaphragm of the control valve. Okay. A pneumatic output in the form of a pressure to the valve top PV will go. Okay. This will actually give the proper position of the control valve. So, this is all about the positioners of the control valves, and the control valves and most of the you see the most of the figures actually we have taken from the Fisher's control. They are the largest manufacturer of the control valves. This is available in the websites. There is no problem. If those who want to look at the details of the figures, they can go to the particular site and look at those figures, right. And with this I come to the end of the lesson 39 of the industrial instrumentation.